right, thank you for having me. This is Benne Holwerda, and I'll be talking about supernova host galaxy dust extinction evolution. So that's a whole word soup together. I'm from the University of Louisville. I'm doing this together with Katie Mack, Alice Jacques, Justin Hill, and Wade Rumer, and many people in the GAMA team. So I'll give you a short motivation. Supernova distances are one of two cosmologically mainstay methods. So the main uncertainty for those remains the host galaxy, the galaxy that these things are happening in, their extinction. Evolution in the host galaxy extinction could mask or mimic cosmological results. So really this is something that we need to control for. As it happens, I like dust, I study dust in galaxies, so this is how I got interested in this. And there is a tension between the supernova 1A results and the cosmic microwave background results. So maybe this is something that is a mitigating factor or possibly exasperates it, we don't know yet. How do you fit a light curve of a supernova? So on the left here, you see the observed light curve, and typically you get a color these days and perhaps a spectrum as well. And so as a function of time, the light curve, the supernova brightens and then dims over time. Then you need to do some kind of probability fit where you have two kinds of priors. You need a probability for the amount of dust extinction. That can either be the green line, which is that every possible level of extinction has the same probability, yet we sort of know that most galaxies are exponential-ish. So you can also do an exponential drop-off where the most extinction actually has zero probability of happening. And there has to be some sort of probability and an intrinsic distribution of color. And so you combine all that into some kind of probability fit and you get a distance modulus to the supernova. Now, the big question for me is, what is the actual shape and the evolution of that prior of dust extinction by the host galaxy? Now, that's pretty important because this is the summary slide where I try to explain what happens if you put the supernova in different parts or different kinds of galaxies. So the dotted line is the exponential drop-off that we've been using for every supernova ever observed. So it's all an exponential drop-off. That's our expected prior, and it's a pretty good one. So suppose you're the red supernova, you're in a typical galaxy, and the probability function that you actually follow is pretty close to the exponential drop-off. You're going to fall right on the Hubble law, the Hubble diagram in the top right corner. Your distance is going to be correct, and therefore it's going to be at the right redshift distance point. However, if you're in a bigger galaxy, there are going to be regions with much more dust, with much more ISM. The probability of actually hitting one of the denser clouds is going to go up. So you're ending up with a blue kind of probability function. So on the whole, you'll end up underestimating the distance. However, if you then move the supernova out, so to greater distance, the supernova host galaxy distance is a little bit further, then you can imagine that the probability function starts to shrink a bit. So this is, in short, what I'm after with a much larger project. This larger project uses overlapping galaxies, and these overlapping galaxies, as you can see here, the foreground galaxy is a small one. It's a 10 to the 9 solar mass galaxy. It's a nice disk. You can see that it has this big beard of dusty, fluffy stuff around it. These galaxies are not interacting. It really looks that way, but we can only see it now that we've put a bright galaxy behind it. So that acts as a light table, as a clear background light to highlight where the dust, the interstellar matter of the foreground galaxy is. So that gives us a measure of how much extinction there are, how much different values of extinction there are in the foreground galaxy. I really love this picture because all the stars that you see here, they're not in the Milky Way, they're in another galaxy altogether. These are in NGC 253. So we're seeing through a galaxy, out of galaxy, that we're looking through at a galaxy behind that. I love that. Astronomy is awesome. So here's a couple of these examples where we have overlapping galaxy pairs, and we've done measurements in where we got good signal to noise, so basically where we got a good background source, and then we get these distributions of extinction. And as you can see, there's already a bit of variance, even in the 3 samples that we have so far. And that depends on maybe mass, maybe on separation, or like how far out in the galaxy you are. So we have these three distributions, the blue distribution, the orange distribution, the green distribution, and here is the line that we've been using for supernova. You can kind of see that if I stack all these galaxies together, we can sort of get something that averages out to this exponential. But we are interested now in individual supernova distances. We want to get those errors down. And so if that's the case, then we probably want a bespoke prior for every kind of host galaxy. That's the ultimate goal. And so we've got these different mass galaxies and different inclinations, and maybe that we can find a bespoke prior for dust, for host galaxy dust that way. So Jia in 2007 nicely showed that if there is if you assume an exponential drop off of a certain prior, and that prior is that tau is the drop off, the exponential drop off for the values of extinction that you can expect. If you assume the wrong prior, you actually get a slight deviation of your whole sample in the distance modulus. So I've been using this relation, saying like, all right, if I've got an exponential drop off of some description, how off am I? How much is my distance going to change with my probability fit? And so I can start here, and then I end up at 0. That's the one that's been assumed so far. But if I, for instance, incline my disk a little bit, I'm going to actually move that exponential drop off left and right. So that's actually a SNIa function. Okay, fine. I've got inclinations, I've got stellar masses, and I've got radii, supernova, the distance between the host galaxy center and the supernova. And I've matched these to my 3 drop-offs and said, okay, this is the exponential drop-off that is representative for that particular galaxy. And if you do that, the mass-matched sample actually reduces the residual in the supernova fit. So that's indicative that stellar mass is probably the driver. That's how we should bin our galaxies. Bigger galaxy, more ISM, different kind of prior. Okay, so that's what we found so far. But that doesn't give you any evolution at all. It essentially says, okay, we're matching to a local template, and is there any evolution out to redshift, 2, say? Because all this action happens with supernova, well, basically in the last 1 or 2 between Z is 2 and now. And so what kind of evolution happens? Well, we also know that star formation peaks at redshift 1, 2, and then drops by a factor 10 all the way to redshift 0. So how does the dust content of galaxies change? How does dust geometry change? That's something to go and explore. Now, very recently by Simon Driver and the GAMA team, they put together 3 different surveys, the GAMA survey, the G10 or the Cosmos survey, and the 3D HST survey. And together, they actually cover all the way out to redshift 5. And the nice thing is that they are all 3 of them are multi-wavelength, meaning that we can start doing spectral energy distribution modeling. What is that? Well, here's the 3 surveys. We've got GAMA, which is the blue, red squares. That's all the galaxies that we got from those. Then purple is the Cosmos field, and in that is the G10 field. And then even smaller than that is the Hubble field, that is a 3D HST. So funny enough, because of the fact that we're basically looking at a cone, the 3 surveys roughly cover the same volume. And so we're staying pretty constant as far as volume is concerned and completeness. So what we then do, what Simon Driver and his team did, was to fit the SED so that you can see the wavelength. You can see a spectrum here with how much emission you get from a galaxy as a function of wavelength. This is the rest frame wavelength. You see a lot of reprocessed starlight ends up as dust at around 100 micron. So if that's the case, we should see the emission from dust at every redshift. And we do for each individual galaxy. So every galaxy in these surveys, with all the photometric points and a spectroscopic redshift, we get an SED fits to all these different galaxies. So we get dust masses, stellar masses, and star formation rate. So the stellar masses are pretty complete, out to the star formation rate, sorry, so at the top, stellar masses in the middle. Stellar masses go from 10 to the about 7 to 10 to the 12, and then dust masses kind of go from 10 to the 4 to 10 to the 9. And the interesting thing is that we can see these two about redshift 2. The survey combined, these three combined, are pretty complete all the way to redshift 2. So we have a pretty good census here. And as we go back in time from left to right, we can actually pick out what the distribution of galaxies and distribution of stellar masses, distribution of star formation rate, and distribution of dust masses are. Star formation, we then integrate everything together into a volume, and then you get a volume density star formation rate. Really, that's like the Maddow plot that we all love and see so many times. And then that kind of peaks at around, redshift 1, 2, so somewhere about 10 gigayears ago. You do the same thing with stellar mass volume density that steadily climbs and sort of plateaus at redshift 1 as star formation sort of has its heyday. Now with dust, the interesting thing is, because now we're interested in the life cycle of dust, star formation both produces dust in supernova and AGB stars, but it also consumes dust, because that's what the giant molecular clouds that drive star formation are made of. So really the lifetime of dust is actually assumed to be pretty short on galactic scales of about 150 megayears. And so the volume density of dust in all the galaxies is fairly flat-ish, but I did notice that there was a bit of a peak around redshift 1, which is also where we see a bit of a peak in the supernova rate. And so the fact that I just sort of squinted and saw two peaks, that got me going on seeing if this could actually help with the supernova problem. So here's the various models for how much dust there is in a given volume, right? So we're now not even wondering about where it is in the galaxies or where it is in which galaxy. It's just, it's in a box. And how much dust do we have sitting in the box? The models are still not entirely constrained and not entirely in agreement with the data. So there's a lot to be done here. But I'm interested in seeing if I can do anything about the supernova that we see here. Instead of the Hubble plot at the top, I'm looking at the residual after I've subtracted the flat cosmology. So MAGPHYS assumes a disk geometry. I'm just going to have to live with that. And so how does the changes in the average dust density change the supernova 1A bias? Oops. Here we go. So how can I drive tau, basically? And so what drives that particular value back and forth? What's the average value at a given epoch, or what's the distribution of values at a given epoch? So starting with that, let's say, well, what if tau is just proportional to the volume density of dust? First order doesn't strike me as too odd, and you can see in the Rees 2007 data there's a neat little peak at redshift 0.5, and that's roughly where we saw a bit of a rise in the dust as well. The thing is that if the relative change in dust volume would drive tau, the actual difference isn't that big. And we see there's much bigger changes in evolution of galaxies. For example, their size grows quite significantly over the same period. So we could you can imagine tau being driven by galaxy size, for example. So of all these things, which one is the best? There is really no best. So that seems to be pretty inconclusive. There's nothing that seems to correlate that well. I also looked at the other things that MAGPHYS produces, like could that tau of the prior be proportional to the relative star to dust mass, or for instance, the fraction of cold dust? How much of this is in dense clouds? How much of is in warm dust, like is in diffuse cirrus? How the temperature of the dust that we find, or in the average optical depth that MAGPHYS finds? And really, all these things don't seem to agree. They don't think, if I correct the supernova for this, they don't suddenly agree better with any of the cosmological models, the cosmic microwave models. But each galaxy has a central optical depth. So every single one of these points represents a dust mass, which also can be translated by MAGPHYS as an optical depth at the V band, at the rest frame, at the center of the disk galaxy, of the disk of the dust disk. So we have a distribution of optical depth values at each redshift. At each redshift, as you can see here, the x-axis, and then looking at the optical depth, the central optical depth for each of these galaxies, you can see that the distribution is essentially an exponential as it goes to higher values. So I made a little movie out of that. Essentially, the thick gray line is the data, and as we go step to higher redshifts, you see that both the exponential and the log normal fit to them change a little bit as far as what the central drop-off is. So we do see evolution in the population of galaxies, like let's just assume that all the supernovae happen in the center of galaxies. Even if that just happens, we do see evolution in the amount of dust extinction, the distribution of dust extinction that we observe. So if we do that and say, okay, that's our prior as a function of redshift, complicated plot alert. So the triangles are if we assume that the log normal distribution is a little better description. So mu and sigma are the mean and standard deviation of the log normal plot. They actually don't improve, but if we say, okay, fine, the prior is simply the T naught that I fit to the distribution of central optical depths that I found from MAGPHYS, it does improve our agreement with the cosmic microwave backgrounds, which is I plotted WMAP 7, WMAP 9, Planck 2013, Planck 2015. And as you can see, the CMB values kept going away from where the mess of supernova dots are, but we are actually moving the dots a little bit closer, or at least in some cases. So the plan was to see if that, what the deviation, the chi-squared, the separation between these two is. And maybe you can see this here from both either the binned Pantheon data or just all the Pantheon data combined. And you can see that if I correct using the optical depth distribution of all the SED fits at the particular redshift, there's a slight improvement towards the Planck results. So we're sort of bending a little bit towards the Planck results. Is this the smoking gun? No, but I think this is very much pointing to that the actual prior, the distribution of values that goes into a supernova fit at redshift 0.5 should very much be different than one that is found for redshift 0. And we should tailor those. If we really want to get down to 1% accuracy for supernova distances, then yeah, you need to give each supernova, see what its host galaxy is like, see what stellar mass it is, and say, okay, for that redshift, you need this prior. There should be an evolving prior for these things. All right, so the conclusions are the supernova are dimmed by the host galaxies. That's definitely happening. This likely skews the distances some. SED models of galaxies produce a distribution that definitely evolves with over time. And their evolution accounts for some, but definitely not all, the discrepancy with the CMB cosmology. But this would be a way to make things less worse. I am certainly looking forward to coming up with more overlapping galaxies so that I can find more extinction probes. And so I know more shapes of the actual distribution in a galaxy. But for now, the central optical depths that I have will definitely do. So thank you very much for your time. And I will go and hit stop.